A lens is an object that has curved sides and is transparent or translucent, so it allows light to pass through it. Different lenses have different shapes, and this causes the light that passes through them to be refracted in different ways. Many optical devices use lenses, including cameras, magnifying glasses, binoculars, microscopes, and of course, spectacles or glasses. There are also lenses in your eyes. There are two types of lenses: convex, sometimes called converging, and concave or diverging lenses. A convex or converging lens is curved outwards on both sides. It's represented on a ray diagram as two arrowheads pointing outwards joined by a line. It's made of a material denser than air, so as light enters it, it will slow down and bend towards the normal. As the light leaves the lens, it's refracted away from the normal. As a result of these refractions, parallel rays of light entering the lens converge and meet at a point. This point is called the focal point or the principal focus. The distance between the focal point and the lens is called the focal length of the lens. The principal axis goes right through the middle of the lens. Light travelling through the very centre of the lens isn't refracted. A thicker convex lens will have a shorter focal length because the light is more strongly bent or refracted. Also, the higher the refractive index of the lens medium, the shorter the focal length, because the light will be bent further away from the normal. Position and nature of the image formed by a lens can be found by drawing a ray diagram. Two rays of light are drawn from the same point on the object. One ray is drawn parallel to the principal axis. This gets refracted towards the focal point. Another is drawn through the centre of the lens, so its direction doesn't change. An image is formed where the two rays cross on the opposite side of the lens to the object. When the object is a long way from the lens, as in this ray diagram, the image is real, inverted, and smaller than the object. When the object is close to the lens, as shown in this diagram, the image is real, inverted, and larger than the object. Convex lenses are used to magnify things. You can work out the magnification produced by a lens if you know the size of the object and the size of the image. Here's the formula. If the magnification works out at less than 1, then the image will be smaller than the object. A magnification of 1 means the object and the image are the same size. Let's look at an example. If the height of an object is 15 millimeters and the height of the image is 30 millimeters, then the magnification is 30 divided by 15 is 2. We can show how a converging lens magnifies an object by drawing a ray diagram. The rays are diverging. The only way to see the image is to look through the lens. Tracing those rays back, we see we get a virtual image. It's virtual, upright, and magnified. Now let's look at concave or diverging lenses. These are curved inwards on both sides, thinner in the middle than at the edges. Light travelling through them is diverged. It spreads out. A concave lens is represented on a ray diagram as two arrowheads pointing inwards joined by a line. Because the rays don't converge, this type of lens has a virtual focal point. If you follow the rays back to where they look like they're coming from, they meet at the virtual focal point. We know, though, that the focal point isn't really there because the rays don't really meet at it. This can be shown more clearly using a ray diagram. Remember, one line horizontally through the lens that gets diverged, another line straight through the centre of the lens doesn't get bent at all. To summarise, with a diverging lens, it doesn't matter where the object is. The nature of the image is always the same. It's virtual, upright, and smaller than the object.